Hello everyone, I'm Peng Bo from Sun Yat-sen University, and I'm very glad to introduce our approach of mining linear temporal logic specifications, namely PURLTL. First, I would like to introduce the problem we focused on. LTL specification mining is to mine LTL formula, which describes the system behaviors from traces. These traces usually come from software logs during testing. The input of the problem is a set of traces, and the output is an LTL formula. Here is an example. There are two traces. The first one is AABC, and the second one is BA. The formula is A until B. That both traces would satisfy this formula. There are two major challenges in this problem. The first challenge is the large search space. Traditional approaches of this problem usually have exponential complexities. To reduce the search space, these approaches usually require a formula template. Therefore, they are not able to mine arbitrary formula. The second challenge is that in practice, the traces are usually noisy. The noise may come from buggy programs or partial profiling. Lots of traditional approaches failed with noisy traces. The key idea of our approach is to design a neural network simulating the LTL path checking. After training the neural network with sampled traces, we interpret the parameters of the neural network to the LTL formula. So let us start with LTL path checking. Suppose that we already have an LTL formula. The path checking is to input a trace and output a binary label indicating that if the given trace satisfies the formula or not. Here are two examples. Suppose that the formula is A until B. The first input trace is AABC, and the label should be set. The second input trace is ABAC, and the label should be unset. Since the original LTL semantics requires infinite traces that are very hard to acquire in practice, we modify the LTL semantics so that the traces are finite. Please refer to our paper for details. Our neural network simulates the LTL path checking. It has a set of trainable parameters. Input a trace and it will output 1 or 0, indicating the trace satisfies the formula or not. We do not know the target formula, therefore the parameters are randomly initialized. Then we search the parameters by training the network. After training, we can interpret the parameters to the target formula. Most popular neural networks are black boxes. It is very hard to explain their parameters. However, our network is a white box. Each parameter has its meaning, and that is the reason of why we can interpret the parameters to a formula. Our network works like a recurrent neural network. It checks the trace from the back to the end, from the back to the front. An LTL formula can be parsed into a binary tree. The parameters of our network represent the structure and the node information of the tree. Due to the time limit, please refer to our paper for details. The detailed interpreting algorithm is also provided in the paper. If you are familiar with the machine learning approaches, you will find a critical issue. Our neural network works like a binary classifier. Training a binary classifier usually requires both positive and negative samples. In this case of mining LTL specification from traces, it is very hard to get negative samples. Our solution is to apply positive and unlabeled learning to our approach. We can use real software logs as positive samples. Then we randomly generate some traces and use them as unlabeled samples. Finally, we apply a variational PU loss to the training procedure. The overall procedure of our approach is shown in this figure. First, we sample some positive traces and randomly generate some unlabeled traces. We input these traces into our neural network, calculating the loss and optimize the model. Repeat the training procedure until the loss converged. Then we interpret the model parameters and output the LTL formula. Let's see the experimental results of our approach. We use 8 benchmarks that were widely used in previous works. Each benchmark represents a common pattern of the software behaviors. Of our competitors are Texta and GLTLF. Texta is a popular traditional search-based approach. It has excellent performance, but it requires a template and it cannot deal with noise data. GLTLF is a previous state-of-the-art neural-based approach. First, we test the performance on noise-free data. Templates are applied to all 3 methods. We modify the source code of GLTLF in order to apply templates. The results show that Texta successfully mine all formula, while our approach mine most of them. Second, we test the performance on noisy data. Texta cannot work with noisy data, therefore we only compare with GLTLF. We add noise by modifying the trace randomly. The noise rates indicate that how many traces are modified. However, randomly modifying traces may not result in the flipped labels. Therefore, the noise rates do not represent how many samples are with wrong labels. We can find that our approach surpasses GLTLF no matter what the noise rate is. Then we take the ablation study of the VPU loss. We replace the VPU loss with the mean square error loss and compare the performance. We can find that in most benchmarks, VPU setting has better performance compared with MSE loss. Finally, we test the performance of our approach with and without template. We can find that the performance drops a lot without template input in some benchmarks, but remains a decent performance in other benchmarks. As a conclusion, we propose an approach to mine LTL specifications, namely PURLTL. Our approach has 3 major advantages. First, it has high efficiency compared to traditional search-based approaches. This is due to the polynomial nature of neural networks. Second, it is able to accept noisy inputs. Third, templates are not necessary for our approach, which means that our approach can mine arbitrary formula. That's all of my presentation. Thank you.